Hello, welcome to the Lec03 class meeting through Teams. I hope you're all warm and safe. We'll just give 2 more minutes to see if others will be joining. But in the meantime, I want to know if there are any questions about the project component that I plan to introduce. Any questions, something's not clear, something that you would like to discuss or ask, or maybe you have some concern, whatever it is, kindly speak up. Is the description that I wrote very straightforward, that you are aware of, like you are clear about what is going to be there, and you think 15% is enough, or maybe if people want to de-emphasize the exam further, maybe go up to 30%. What is your thinking?
I like the fact that our final is more project based and more kind of hands-on. Um, what's the word I'm looking for? Proof, I guess, of what we learn throughout the course. Because when we work in real life, we're not going to be writing exams. We're going to be doing projects.
So you like the project, okay? So for those who have not had a chance to look at it, the project is essentially that you take a funnel. I plan to buy some funnels and give it to you guys. Fill it to the top with some viscous liquid, and then start letting the liquid discharge through the funnel. Have a camera, record a video, and monitor the time it takes for the funnel to go from full to empty. That's the discharge time. And also, if it is a see-through funnel, you should be able to see where the liquid level is at different time points. Get that from the video frames, so that you can have H, the height of the liquid, as a function of time. And on the modeling side, you're going to use control volume analysis, which we will see in the course, to essentially calc or develop an equation that predicts the total discharge time as well as H of T. So from both of those, you'll be able to say what is the whether you are able to get agreement with your analysis, the model, and the experiment, which is the data that you collect. So it's actually a very straightforward concept. Do an experiment, get data, do modeling, get an equation, see if the prediction agrees with the observation. Okay, so I got a couple of people saying they would like to have a hands-on project, but I didn't get any specific feedback on whether they like this particular project or they want something else within fluid mechanics. I wasn't sure, but this I thought is a project that I could assign with minimum resources. You could take hand soap or some thick viscous liquid like maple syrup that you can find at home and do the data collection. You don't need very lot of costly materials to do this work. That's why I went with this. So if there is any concern that you would express, now is a good time. Otherwise, by Thursday, I hope to finalize and post this. No concerns. You're okay with this?
I'm good with it.
You're good. Okay. Others, at least a vote of yes, saying yes, this makes sense. I would like to do this.
Yeah, I'm good with it.
Good. Okay. Thank you. Okay, so if this project is included in the course, we are going to have a grade structure that looks like this. There will still be 3 midterm exams. I might not have like some questions covering explicitly Unit 1, because the experiment that I'm proposing with the funnel is really something that draws concepts from Module 1. So we won't have a separate quiz on that. There will be 3 exams covering 2 modules each, and then there is the final, which I said was originally 45%. Now, if the project is worth 15, that would become 30. And I'm inclined to make the project go up to like 30% so that the final is just another exam. So there is less pressure. You can show up, take the exam, and basically it's a demonstration of what you have learned throughout the course. And the project becomes something that's hands-on and it will test you. I'm pretty sure that's how I designed it. So in my objectives, your objectives, both will be satisfied. Sound good?
I don't know.
Hmm. Yes.
I don't know about like a full 30% for the course project, but I would be fine with like 20%.
20%. Okay.
Yeah, I was
So
thinking-
these exams, they contain 5 problems in 75 minutes. This one contains 6 problems in 120 minutes. So I'll try to tweak this. It won't be 15. It probably will be something between 20 or 25%, and project will be remaining. So that would make this what? If this is 20, 65, 75, that would make this between 20 or 25%. Is that okay?
Yes,
sir.
I like that.
Yeah, I would say that's better.
Yeah, yeah. You don't want also to become whatever is the higher percentage will become the pressure item, right? So you want to keep all of them around the 20% mark so that you feel good about working on them. I'll try to ensure that. Okay.
I have a question, please.
Yeah, sure.
So for the project, I don't remember when you said the due date was.
Study day. The report will have to be turned in by study day.
Okay.
So that
And-
in the last week, you don't have to deal with both project and final.
Okay. And my second question was, with like essentially kind of like the questions we're answering about the fluid system that we're going to create, are they going to be organized in such a way that as we go through each section, we'll be able to answer them more completely so that we can start maybe working on them now? So
Yeah, I mean, my hope is that to get you to do the hands-on work of setting up an experiment like a camera, funnel, liquid, and doing the image analysis. And on the modeling side, doing some derivation for the exact geometry of the funnel, taking into account the viscosity of the liquid, doing some actual derivation using control volume analysis. The report writing part, I will release a template. It's just essentially like, let's say 3 or 4 pages. It will have specific questions or sections where it'll say, enter this information and there's a blank or some given space exactly telling you what's needed. So you just fill that out and that's it. You don't have to write a free form report, which will take much more time.
all right, thank you.
Yeah, the goal is not to get you too drawn into report writing. The goal is to make you do some, gets your hands sticky. All right. Okay, so let's move on. We have been discussing about fluid properties. We have previously discussed up to section 1.5 in the textbook, which covers ideal gas model. This was the last thing I talked about last time we met. So P equals rho RT is the ideal gas law or model. It's the equation of state that constrains the state variables, pressure, density, and temperature of a gas under specific conditions or assumptions. The key, there are a lot of assumptions. We're not reviewing all of those. We don't need all of those, let's say. But the most important assumption is relative to the condensation point of the gas, the temperatures P and T involved need to be low pressure as well as high temperature. Like for example, if you're thinking about steam, using this equation for superheated steam, it has to be much hotter than the boiling point so that the chance of it condensing back is very low. As well as you can take nitrogen at room temperature and pressure, because nitrogen's condensation point is very low. It's actually exactly around minus 196 degrees Celsius at 1 atmosphere pressure. So if you're dealing with 1 atmosphere regular conditions at, let's say, room temperature, nitrogen is a gas, and ideal gas is an excellent model for nitrogen. Always check whether the pressure and temperature are consistent with this key assumption of the ideal gas law, which means ideal gas law cannot be used for cryogenic or low temperature gases. It can definitely not be used for liquids or solids. Don't make that cardinal mistake of using ideal gas law to get the density of a liquid such as water. That would be very wrong. So if I ask you a question, then how would you get the density of water at a specified temperature? Any answers?
Would it be its mass over volume?
Yeah, you'll have to look up a data table where people have actually did a measurement of weighing a known volume of water, recording its mass very precisely, and then telling you what the density is. That's the only way to know the density of a liquid if you were to look it up. Okay. So the message is don't use ideal gas law, especially for liquids. It's completely inapplicable. Clear? All
Sure.
right. I see that there are a lot of people, but nobody is willing to come on camera. Can those who have a camera, will you please come on with your camera on? That'll help me to have some conversation and know that there are some people on the other side. Please, it's a request. Whoever can, please do that. Okay, moving on. The next important property, thank you, Eli. The next important property we are looking at is section 1.6, viscosity. So viscosity, you have a lot of daily experience with viscosity. Can you use some simple words to tell me what it is? Simple words. Don't use any technical word like shear or anything. But what is viscosity in your thinking?
The thickness or like flow rate of a fluid, like how easy or uh, resistant it is to flow.
Okay, so when you said thickness or flow rate, what you mean is it is like the tendency of the fluid, or it's to resist flow, or we can say a measure of how easily the liquid can flow, correct? Or fluid can flow. Can we say that?
Yeah.
Okay.
Yeah.
Any other responses? Thank you, Trey. Thank you, Wami. How else will you be able to explain viscosity to somebody who is not a, let's say, a mechanical engineer, somebody who's, yeah.
Fluid stickiness.
Stickiness, okay. Stickiness is not exactly viscosity. Yeah, it maybe it kind of is. Stickiness, or actually what you mean by stickiness is kind of what he said before, because if it is sticky, it's going to resist flow. That's what I think you mean, correct? Okay, good. All right. So the book talks about viscosity in a little more formal way, and we'll see that. So we talked about fluid. Can you recall what the definition of a fluid is when we saw that 2 lectures ago?
A substance that deforms continuously.
Very good. Substance that deforms continuously and also irreversibly when acted upon by a shear force or stress with no minimum threshold. Okay. Now, when we talk about, let's say, two liquids, consider two liquids. We'll take the familiar thing that we all know of, which is water. Okay. And we'll take, can we tell something that's more resistant to flow or more viscous than water? What can we think?
Honey.
Honey. Perfect. Honey. Consider two liquids, honey. Okay. So if you do an experiment that looks something like this, let's say you have an inclined plane. Okay. You have an inclined plane, and you have a dripper which constantly drips water, and then another dripper which constantly drips honey. Okay. And they both start at the same time, and they start, sliding down or flowing down. Which do you think would have flown for a longer distance under this condition, where this incline is, let's say, some angle from with respect to the horizontal?
Water.
What this would be water, right? If I didn't label this, you would come in and say this must be water and this must have been honey. If you are if you are the forensics person coming in and investigating something, this is honey, this is water, right? Trey, can you tell us why honey would have flown to a lesser distance?
Well, it's because its viscosity is a lot higher than water's.
Actually, it should you should be
Or,
said
yeah,
it should be said the other way.
Yeah.
Because it is very sticky and resistant to flow, we consider it to be more viscous than water. Does that make sense? Why I'm inverting the way you say it?
Yes.
Viscosity is a number. You can define a number. The number doesn't make it more resistant to flow. The fact that it is more resistant means it has a higher number.
Right.
Right?
Yes.
Right. So we will say that honey is more resistant, or we call it more viscous. Okay, so it is consistent with this definition we got before, that it is the tendency of the fluid to resist flow under the same driving force. Like these two liquids are experiencing the same gravity, same incline, same force, whatever there is sliding them or flowing them down, but one flows a lot further than the other because this honey resists the flow or the force more than water. Okay. So it's time for a formal definition. Okay, so let's go back here. All right. So formally, viscosity. I'll maybe write this in the next slide. Formally, viscosity is defined as the ratio between the shear stress, which is causing the flow, and the velocity gradient that is caused by shearing of layers. I introduced a term that I didn't define, but I'll come to that. So that would be, if I write viscosity, okay, viscosity is defined as the shear stress divided by the velocity gradient, and I'll have to tell you what velocity gradient is. Okay, so let's write this down first. I'll write a diagram. So let's say you have a liquid. Okay, here's a surface, a solid surface. Okay, and let's say I have I'll use a different color, and I have a layer of liquid. Okay, I'll denote this red with, or I denote my fluid with red. Okay, these are fluid layers. Okay, what is always true about anything and everything? This fluid is made up of atoms or molecules, correct? So if you just think about it, these layers are nothing but molecules that are arranged, not arranged, but the molecules are constantly moving around, but they are kind of in a static equilibrium for now. And then let's say you come in and you start applying a shear stress to the topmost layer. So you apply a shear stress not to the middle layer, not to the bottom layer, but the topmost layer, you apply a shear stress, and these molecules that are in the topmost layer, they will try to move along with you, and they will be displaced, and they would have made some motion along the layer of the along the shear stress. You can imagine that if you shear the liquid, the molecules are displaced along the force. Okay, if that is happening, what is the consequence of that to the neighbors of these molecules beneath them? When they move along, what do you think they'll do? What did I tell you about the nature of the force between these molecules?
You're also applying some kind of shear to the layers beneath.
Henceforth, don't use the word shear, but tell me literally, when these molecules take a step to the right, what will happen to the neighbors beneath them, in the layer below?
They're like dragging them with them.
They are dragging them because we told you that molecules, if they are at a certain distance away, unless they are very close, they generally attract each other. So if this molecule goes away, what it does is it tries to attract away the layer below that. So if the top layer travels some distance, the bottom layer is dragged along. The next layer is also dragged along. The next layer is dragged along a little less and a little less and a little less and so on. So over time, what will happen is the velocity here of this top layer will be something. The velocity of the next layer, we'll call it V1, V2, V3. As you go down, the velocity decreases. So velocity, here, velocity of subsequent layers decrease. Do you agree with this? Because of the intermolecular forces, and dragging of layers below. Do you agree with this? Yes? No? Okay. So this shear force, which is the cause. Okay. Remember the word cause and effect. Okay. This shear force, which is the cause, causes a velocity that is changing along this vertical direction. So if I call this direction as y, this velocity is not constant along y. Do you recognize that? So if something is changing along a certain direction, we call it with what term? What is the name of that change? If the velocity is changing along the y direction, it is a gradient along that direction. So we call it a velocity gradient, which is the cause due to shearing. You do shearing, that is something you do. What you observe as a response from the fluid is the setting up of a velocity gradient or the formation of a velocity gradient. Okay. So this shearing is something that you control. Okay. This is external, meaning it could be you, it could be a machine, it could be a surface, it could be a brush, it could be a machine tool or whatever it is. This is external, which means you can set the force, and depending on what the fluid's internal mechanics is, or whatever its nature of the fluid is, depending on the molecular structure, all the gory details we don't want to know, the velocity gradient is an effect that we observe. You do the same experiment as before with honey and water. The same force is causing a lower velocity gradient in honey, whereas it is causing a higher velocity gradient in water, which makes honey more viscous than water, which is consistent with this equation here. In honey, this velocity gradient is lower, which makes the viscosity higher, and in water, it's vice versa. Okay, so this definition here is for the quantity called dynamic viscosity. Okay, it talks about viscosity as a ratio of shear stress to the velocity gradient developed in the flow. I'll call this effect. I'll call this action. Sorry, yeah, cause and effect, cause. So this is the definition you want to use. The viscosity is the ratio of shear stress to velocity gradient. And then if this ratio is constant for all values of velocity gradient, that is, sorry, all values of velocity gradient, then, okay, before this sentence, I need to say du over dy, the velocity gradient can also be interpreted as the, as the rate of shear strain. Okay, rate of shear strain. How? We all know what is strain, right? You know what is strain? What is strain? Change in length divided by original length, right? From mechanics of materials. Yes, no? Right? Strain is change in length divided by original length, right? So when you have a layer of fluid, let's say you have a solid surface, and then you have a layer of fluid which is getting sheared. Whatever a molecule that is here at one instant is displaced to another location. So if you take this angle, okay, this angle here, we'll call it delta. Okay, this delta is going to be, I'm sorry, this angle. Sorry, I need to use a different nomenclature that's consistent with the book. So I'm going to use this angle is denoted by delta beta, and this length is denoted as delta A. Okay, and this distance is denoted as B. So tangent of delta beta is equal to delta A divided by L. That is just trigonometry. Ratio of opposite by adjacent is equal to tangent. And since this angle is small, we'll approximate this as tangent of beta is delta A divided by L. Okay, delta A divided by L. With me so far?
So is the shear strain the hypotenuse of the triangle, or is it delta A?
Delta A. This is the change in length that you are producing.
Okay.
Okay. So we want to get, see, okay, think about delta A. If you are moving this top layer at a certain velocity, delta A is simply that velocity multiplied by the time over which this is happening. Okay, this is, see, if you are applying a shear stress and you are causing the top layer to move, how you would know that it is actually moving? You would observe the velocity of that top layer because you control it. It could be a rotating surface, or it could be your hand, or it could be some surface or a boat which is causing that shear displacement at a certain rate. We'll call it U, velocity. Okay, so we'll write that delta beta, I'm going to continue this. Delta beta is equal to delta A divided by B, which is U times delta T divided by B. Okay. Remember, this delta beta is the angle. Okay. So we'll write delta beta divided by delta T is equal to U over B. U is the velocity of the top layer. And B is the thickness of the layer. Okay. So this is the rate of change of the angle So this delta beta, okay, this delta beta is the rate of change of angle. I'm sorry, is the change in angle. And when you divide that by the time taken, that becomes a rate. Okay, it's just calculus going from a quantity to from a change to a rate. And in the limit that you do this for a very short interval of time, this delta beta over delta t, I'm going to use the symbol with 3 lines, is defined as gamma dot, the strain rate. Okay, it's defined as the strain rate. Okay, so this quantity, strain rate, is the rate at which that angle changes. But according to this equation, this is also equal to U over B. U over B. All right. Can I switch to the next slide? So we are at what? We are at that point where we are writing strain rate is equal to U over B, which is like saying here is a layer of fluid with the top layer moving at U and the thickness of the layer being B. Okay, there are multiple layers. Okay, and it doesn't make sense if B is really large. B has to be something that is differential. So in the limit that, or we make this very small, we make this small. Why? So that gamma can be defined at any point rather than for a finite layer, for any point than for a finite layer. So that said, gamma dot is equal to du over dy. For a small change in velocity and a small change in vertical height, the ratio of those two is the strain rate. So strain rate is directly the velocity gradient. So whenever we use the term du dy, we are referring to strain rate directly. So these two terms are usually interchangeable. Whenever we say velocity gradient, it could also mean strain rate and vice versa. Okay, so we have tau equal to, sorry, oops, mu, we have mu is equal to tau divided by du dy. This is the definition of viscosity. Definition. More commonly, if viscosity is known, we write tau is equal to mu times du dy, because this becomes a known property that you can look up. If you are doing this for the first time, yes, you need to do an experiment to figure out the viscosity of a liquid or a fluid. But if that fluid data is already made available to you, you can treat viscosity as a known property of the fluid and then measure or calculate what the velocity gradient is, which then becomes an equation for shear stress, a way to estimate the shear stress. And this ties back to the original experiment that I talked about, where we have a water dripper and a honey dripper. The honey flows to a shorter distance than the water because for the same shear, the honey is more viscous. It gets you a smaller velocity gradient and vice versa for the water. Okay. Questions before we go on to classify fluids based on their shearing behavior. Is it clear, not clear, intuitive?
Mhm.
So, Kwame, you said you work with biomedical projects or something, right? You like biomedical something.
That's right.
So when they say the classic phrase, blood is thicker than water, what are people referring to? Is it the density or the viscosity?
Probably have to be the viscosity, but I don't think that's
Think about that, because thick means it could also mean it's heavier. Um, but yeah, think about it. But we have introduced one important property of liquids, which is viscosity. Okay. So what do you know about viscosity? That is, I know the word non-Newtonian has been thrown around. Okay. So what do we know about um, viscosity? The relation between shear stress and velocity gradient per strain rate. What do we know already? Can you just say? Anything that comes to mind. You don't have to be exact about this. Don't try to polish your answers. Yeah.
Could you repeat the question?
When we say viscosity, okay, um, let me give a clue. What all comes to mind? How does viscosity depend on temperature? Let's say, if you increase the temperature, will a fluid become more viscous or less viscous?
Um,
I think it's less viscous.
Okay, increasing temperature makes a fluid, especially liquids, makes a liquid, we'll talk about gas separately, less viscous. Okay, good. I agree with you. Why? Why would it make it less viscous? Or why would it make it less resistant to flow, which is what viscosity is?
Because it loosens the intermolecular bonds,
Right.
I guess.
Because thermal energy weakens molecular bonds and makes their motion more random and less resistive to directed motion or shear. Right? Thank you. All right. Um, if you increase the rate of shearing, that is, if you apply a certain so this quantity here, du dy, is called the rate of strain or strain rate because it tells us how drastically the velocity is changing or different between fluid layers. Um, a high value of du dy means rapid motion of the top layers relative to the bottom layers. Would you agree? That is, if this value is high, it means in the vertical direction, velocity is dropping drastically. Okay. Now, what is the unit of du dy? You're all experts in units and dimensions by now, right? What is the unit or dimension of du dy? So how do you get the dimensions of a quantity, which is a velocity divided by a distance? That will be LT power minus 1 divided by L, which is T power minus 1 per second, right? The unit of du dy strain rate is per second. Okay. So this unit or this du dy with units of per second is a measure of how rapidly the fluid is being deformed. Okay, example time. Can you tell me some situations in which the fluid deformation is very slow as opposed to other situations in which the fluid deformation is much faster? Not about resistance. Don't compare honey with water or some two different liquids. For the same liquid, a high flow or a high shear and a low shear, or a high speed and a low speed situation.
When magma is like flowing down a volcano, it starts off very quickly, but then as it cools, it becomes very slow.
Magma is a very it's a fringe example. Can we consider some situations which are more closer or more relatable, like water, involving water, engine oil, something like a hand soap or a toothpaste, something that you can quickly connect with.
I was actually going to mention engine oil. Especially now, your engine oil is more like a gel, and
Right.
then as it heats up due to the work of the engine, it becomes a thinner liquid.
Okay, good example. Let's start there. When you just go get into the car, the engine oil is pretty much like a jelly, and the engine is very cold, minus like 30, 25 degrees Fahrenheit. Now, as you start your engine, can you walk us through what happens that makes this uh, as you start the engine, how is the shear rate low, or as you go on, is the shear rate getting faster? What's happening?
The shear rate is it would be increasing because it is easier to shear the warmer it gets.
So as your engine gets warmer, the liquid becomes less viscous, so it gets easier to shear. But we can nominally say the engine is driving the same is exerting the same amount of stress from the beginning to end. Only that the fluid becomes more or sorry, less viscous as time goes on. Correct?
Yeah.
Okay. All right. Good. So when you think about this rate of shear, that is this rate of shear, du dy can be a constant, or vary with time, meaning it can increase or decrease with time. Okay. Now, when you do an experiment or when you are in control of a situation, what is that you get to do, and what goes into the fluid, and then the fluid does something. So what are you in control of when you are, let's say, you're running an engine, or having a stick, or applying a force? What are you in control of? You are in control of the force that you can exert. you can have some kind of a way to apply more force or less force. You can apply a force to a liquid, and then liquid has its own internal molecular structure and mechanics. So it will have a response, and that's what you see as a velocity gradient. So to get you back there, recall this: the shear stress, which is really a force over an area, is a cause, meaning you do that. It's your action. And then the velocity gradient is an effect. Okay. So this is a matter of observation. So if you look at figure 1.7 in your book, okay, I'm going to paste a copy of that figure shortly. Actually, let me do that right now. If you look at figure 1.7, everybody can see this clearly? Like, is it big enough? Okay, so if you look at figure 1.7, there are some fluids for which the relation between tau and du dy is a straight line. It just remains the same throughout as you keep increasing the force or shear stress, the response of the fluid is the same. But there are then some fluids which get progressively easier to deform, like to get the same deformation. For the same force, you get a larger deformation in shear thinning, and then it becomes progressively difficult to deform, which is shear thickening. To get the same deformation, for the same force, you start getting lesser deformation. Now, why would that be the case? So I'm going to write down what I said. Some fluids have linear or steady response, steady/predictable response to shear. Their resistance, that is their viscosity, doesn't change with strain or with further deformation. These are the ones we call Newtonian. So somebody used that word Newtonian in the very first lecture about fluids and viscosity. I forget the name, but they are perfectly right to use the term Newtonian. But what the term means is the resistance of the fluid doesn't change with continuous deformation. It doesn't get progressively easier or more difficult. It just remains the same where we started. It's like water. Water is a classic Newtonian fluid. And then there are these shear thickening fluids. They get harder to deform as you deform them. Can we get some example? What gets harder to stir as you keep stirring?
Milk.
Really? Does milk does that? I haven't experienced that. Anybody else think that?
If you keep stirring, you get butter out of like.
Oh, that is you extracting or trying to separate the fat and extract the fat, and then fat is sort of like a foamy material. Let's not go there because that is a different process. It's basically separating the components of that colloid. Think about which fluid. It's not actually usually like a single solvent. It's something mixed with something. You keep stirring. After a while, your stick basically is almost impossible to move. You've used this before.
Would dough count in this case, or no?
Dough eventually becomes dough is you start with powder and then all the moisture is somehow absorbed into the powder and then you get a piece of dough, right? That wouldn't really count because you're really starting with powder and ending with something like a ball. So let's not go there. Again, that's not because it's not interesting, but it's a very different topic.
Like a glue?
Louder, please.
A glue?
Glue. Can you please elaborate what happens when you start stirring glue?
The more you mix it, like the stickier it'll get.
Yes,
And
that is, yes, you put a stick and stir the glue. It somehow the molecules, I don't know if they adhere to themselves, but as you move on, they just don't want to go around. It start getting progressively difficult to make further rotations of the stick. Okay, so that will be an example of a glue. You can even try this with cornstarch. If you mix cornstarch in water and then start stirring over time, you will form something that closely resembles jelly, which is what a glue also kind of tends towards. Okay. All right. What examples can we think of for fluids that get progressively easier to deform as you go?
Excuse me, I have a question about the glue example.
Yes.
Is I think what I understood from what you're saying about the milk and flour was that these are like compounds, right?
They are a mixture of several different things. Yeah.
So what's the difference between that and glue? I thought glue was also made up of.
So in the milk example, there is the protein, fat, and also dissolved sugars. What he described was if you keep stirring milk or if you boil the milk, the fat rises, you extract the fat. And what's left behind is pretty much something that's very close to water. It's basically water with some lactose. So it doesn't have very different properties from water, which is Newtonian. So you can stir skimmed milk, you won't see that effect. Okay. The glue, on the other hand, when you squeeze it out of a tube or if it comes in a bucket or something from the factory, it is a liquid, but it is sort of in a state where it is not being deformed. The molecules have a certain initial configuration, and then you start stirring them. Over time, what happens is that the molecules intertwine in a way that makes it progressively harder to do as you keep changing their positions.
Okay.
So if you do this to an extreme, the whole fluid will seize. You'll have like a big cake or a jelly, which can't really be stirred. That's what makes it shear thickening. Shear thickening upon shear. That's what shear thickening is.
Okay.
Okay. Shear thinning is the opposite. What starts off as a very viscous liquid, as you stir it or as you deform it further, it gets easier to do that. That's what we call shear thinning. Any examples?
Would lotion count?
Lotion. Yeah, I would think so. The book talks about paint as an example for shear thinning. I would consider lotion because as you use your hand to spread the liquid, it becomes easier, definitely. So we'll list them as examples. Lotion, especially that which is initially liquid to begin with, not something that is like in a paste-like consistency. Paint. And then there is a class called Bingham plastic. The classic example is toothpaste, where it is a solid until a threshold shear is reached. After that, it behaves like a liquid or a fluid. Okay, so these are all types listed in figure 1.7, which you should be aware of or have a qualitative understanding as you encounter different fluids in real life. And in fact, in the project, if you use maple syrup, cornstarch, or hand soap, or any of these thick viscous liquids, they are most likely not going to be simple Newtonian fluids, but they are mostly like, let's say, shear thickening, somewhere between shear thinning and shear thickening. So they'll have some complex behavior. But we'll the point of the project is to get you to handle them, do a measurement, do some modeling, and learn from that. So it won't be perfect, but it'll teach you something. Okay. Are we okay? Can we move on? All right. Okay, so the next thing we want to know is viscosity has a temperature dependence, and how you would do this is to measure viscosity at various temperatures of interest and summarize the data into a fit for easy use. By fit, I mean like a regression fit. I'm sure many of you have taken numerical methods, so you understand what we are referring to here. Basically, an equation that describes the data. So mu is equal to Ct power 3/2 divided by T plus S. Okay, this equation is called the Sutherland equation. This is what is an example of an empirical fit, not a fundamental law of nature. Can you tell me what that statement means? It's an empirical fit and not a law of nature. What is an empirical fit? What is empirical data?
It's like experimental. This equation was derived from observations.
Exactly. Empirical, very nice. The empirical can also be written observational. It's a fit of observed data. It is not derived from some basic theory or fundamental law of nature, which means there could be exemptions or fluids whose data don't fit this model. As long as the data is available, in this equation, C and S are constants specific to a given liquid or a given fluid, and T is temperature in Kelvin. Okay, so for a given liquid like water, there will be a value of C and S that you can look up and do the calculation for viscosity as a function of temperature. Okay, so if in the exam you are asked to calculate viscosity or use viscosity in a multi-step problem, you will be told, oh, to get the viscosity, use the Sutherland's equation, maybe even provided the equation and the constants that come with it. So you should understand that viscosity has a temperature dependence, and that can be calculated using Sutherland's equation if you know all the parameters needed. Okay, so you don't have to memorize the equation, or you don't have to know the constants by heart, but what you should know is viscosity depends on temperature, and you have to account for it. If you just miss that and just use a viscosity or temperature that is not corrected for temperature, that would be incorrect. Okay. Questions before we move on? So if you look at table 1.8 and also table 1.6, you have the properties of common liquids and gases, which include density, viscosity, specific heat, whatever. Yeah. So what I'll say that tables 1.6 for liquids and 1.8 for gases. Table of density, viscosity, specific heat data. So at least for the practice problems, you need to just look at these and use them whenever you need them. And if you don't have any data in this particular table, there is always the internet. You can look it up and use it in your practice. Okay. Any questions? Can we move on to the next idea? Is this okay? The speed is fine. I'm not rushing you. Yes, no.
No, this is fine.
It's fine. Okay.
Yes.
Thank you, Emiliano. Right. Okay. All right. So far we have been kind of using this word fluid to collectively denote liquid and gas. Okay. It's not now time to ask what is the difference between liquid and gas. Anybody to start the discussion? You know this. Tell me intuitively what is the difference between liquid and gas. Then we'll worry about being exact and everything.
Gas
Liquid
has
has
a
sorry, go ahead. Yeah.
gas has a higher energy state.
Gas has more thermal energy at the same temperature, or in other words, the molecules are loosely bound than a liquid, that they have more freedom to explore around the space. Okay, good. Which is okay. What is the consequence of that? They have more energy, so or more freedom. So what's the most visible difference between a liquid and a gas? You know this.
Liquids have fixed
Gas.
volume.
Liquids have fixed volume, whereas gases tend to, liquid has a fixed volume. Okay, and what do gases do? Gases tend to
Fill whatever volume they're in.
fill the entire volume available to them. If the entire volume available is just free expansion, that is, you just inject some gas into the vast ambient, they'll just fly away in every direction and then they'll just not be there anymore. Whereas liquid, at least if you inject them in let's say you inject some liquid into the air, they will rise up because of, let's say you gave them some initial velocity, and then they'll fall down, form a puddle, and then they'll stay on the ground, okay, at least until they fully evaporate away. But evaporation is a different subject. Let's talk about, if you put a certain volume of liquid, they will have a definitive shape that is dictated by their intermolecular forces and not because they have the entire volume available to them. So if I have a coffee cup, and if I fill my coffee cup to certain volume or certain level of coffee, that liquid is going to occupy only that much volume and not the entire cup. But if I seal this cup and let's say I injected this with some gas like carbon dioxide gas, that carbon dioxide gas is not going to sit at the bottom only like the coffee. It's going to occupy the entire cup, right? You would agree with me. That's the core difference between a liquid and gas. Liquids have fixed volume. And if you consider that this coffee has a fixed mass, it also means they have a known defined density, which is sort of unchangeable, or it doesn't change because of the available volume. Whereas gases, if they can occupy the entire volume, what is the corollary to that statement? It means their density also changes with available volume. You can pack the same amount of gas in a balloon or in a cylinder. You can take the same cylinder and squeeze in a lot of gas and pressurize it to such a high density that you can pack more molecules within the same volume by just squeezing them together, right? So in other words, can we say a gas is compressible? whereas while a liquid is incompressible. What do I mean by compressible and incompressible? Gas density can be increased to a great extent, while a liquid density cannot be changed without some, I'll just put it informally, some Herculean effort. If you have to squeeze a liquid let's say you take a milliliter of water and you want to squeeze it within half a milliliter, you will have to do some ton load of work that is almost humanly impossible or even earthly impossible. You might have to do that only in some very absurd environment or astrophysical environment. Let me ask you another question. We have all used syringes, right? You've used or seen a syringe being used. How does a syringe work? Anybody? You put 5 ml of liquid. There is a needle. Somebody inserts that into the patient's body for an injection. And the whole idea of a metered known volume of dose injected into the patient depends on one crucial concept. What is that? You take a syringe, you squeeze some 1 milliliter and some liquid squirts out. What is the implication when the plunger moves by 1 centimeter or 1 milliliter in volume? How much volume will come out?
1 milliliter.
That's the whole point. That is, it should be incompressible so that if you displace the piston or the plunger by 1 ml, 1 ml of liquid should come out. If suppose instead of that, let's say instead of water, you had air in that plunger and you shut the seal, in principle at least, can you push the plunger? Do you think you'll be able to push it? You'll be able to push it because air is compressible. What occupied previously 1 milliliter, in principle can be confined to 0.5 milliliter if you apply a squeezing force that is strong enough. But for a liquid, that won't work. That's why liquids are called incompressible, because they can't be compressed, whereas a gas can be compressed. Okay. Now, if a gas liquid, okay, liquid is incompressible, right? So we just write it by saying density of a liquid, if we call it by, let's say, rho, is constant for a liquid. It depends only on temperature and not on pressure. If you want to know the density of a liquid at a certain condition, most often the way is to just do an experiment, weigh the liquid, and then get a measurement of mass and volume and get density. For gas, it is different. Yes.
Is compressibility essentially being able to force the atoms of something together without changing its properties?
Yes. It's
Okay.
not. I mean, it's almost that. That is. I'll just say a little bit differently. So we are coming to fluid compressibility. Okay. Compressibility. Just like, let's say, just for clarity, what is elastic modulus? Anybody from your previous classes? Elastic modulus E is what? Stress over strain, right? Any modulus of strength is stress over strain. And as you know now, stress is the cause and strain is the effect. When it comes to length or linear, we talked about elastic modulus. If it is shear force, we talk about a shear modulus. Let's say we call it Y. And Y is equal to what? Shear stress shear stress divided by angular strain. Okay. When it comes to volume, we use the word bulk modulus. Okay. How would you define bulk modulus? By the same analogy.
It's like a radial pressure. It's the pressure all around the object.
It's just pressure, right? Pressure is always normal. And what you're saying is radial all around. At every point, pressure is normal.
Yeah.
And we'll see why in the next unit. It's basically the pressure that you are squeezing it with, we'll call it P, divided by volumetric strain. What is volumetric strain? Volumetric strain can be written as what is linear strain? Change in length divided by original length. What is volumetric strain? Change in volume divided by original volume. Okay, so bulk modulus is like saying for the same pressure, which fluid or which gas will have a larger change in volume. Some gas like helium might be more compressible than some other gas like oxygen or air because of the way the intermolecular forces work out. But as usual, we don't concern ourselves with the details of that intermolecular thing, and we we denote that gas with a simple observable measurable property called bulk modulus, which is again something that is tabulated that you can look up. So bulk modulus is a measure of how easy or difficult to deform a certain gas is. Okay. Quick question. What is, oops, what the hell is this? Okay. Quick question. What is E for a liquid? Based on our discussion so far and this definition that bulk modulus is pressure that is squeezing the gas or liquid divided by the change in volume. What is E for a liquid?
Is it undefined because there is no change in volume?
Well, not undefined. Yeah, you can say undefined, but it's very large or extremely large or infinity, because a liquid does not compress or undergo any change in volume, which will make this delta V. If nothing changes, what is the change? Change is 0, which kind of implies E is practically very high or undefined. So don't think about defining bulk modulus for liquids. Bulk modulus is mostly a property of a gas than a liquid, and it's something that you can look up, and it's what gives compressibility, or it quantifies compressibility of a gas. Okay. So in this course, we are kind of more heavily favored towards liquid. We deal with liquids in our problems more often, but do remember that liquids are incompressible, but gases are compressible, and that is measured using the bulk modulus. Okay.
I have a question again. Sorry.
Yeah, sure.
Can gas be compressed into a liquid?
Yes. If you apply a lot of compressive stress, you can condense a gas into a liquid. But when you remove that, but that may or may not be accompanied with a change in temperature. So it's like saying you are liquefying that gas under room temperature. When you remove that compression force, when you let the gas expand back, it will regain, or it will come back to being a gas phase. In fact, the word compression or expansion essentially comes from gases undergoing liquefaction or not. Anything that is compressed is going towards liquefaction. Anything that is expanding is going towards being a gas. Okay, so this is as much detail I want to talk about in unit 1 or introduction, where these are the fluid properties we realistically need for problem solving in this course. But that doesn't mean this is the end of the story. There are two more important fluid properties. Number one is called vapor pressure, and then number two is called surface tension. Maybe not in great detail, but I still want to touch upon these. What is vapor pressure? How do we think about this? There are some basic aspects about liquids and fluids that you should know, and vapor pressure is one of them. So what is your most common interaction with vapors? Vapor meaning is a term that I specifically use to denote a gaseous form of a liquid, a gaseous form of a material very close to its condensation point, meaning it can go either way. That is, if you have water and you leave it out in the open, it's going to evaporate. But if you put a lid on that, what evaporates from the surface will rise to the lid and start condensing on the lid. So wherever it meets a surface, it just condenses back to being a liquid. So it's sort of in a very convertible form where in one moment it evaporates, it goes from somewhere, goes somewhere else, condenses, becomes a liquid. So it's not like nitrogen. You can store nitrogen, you can transport nitrogen, it will remain a gas. Just because you put it in a cylinder won't turn it into a liquid unless you take effort to cool it. But for water, it's easily condensable, it can evaporate. That's what we denote as a vapor. Make sense? Okay. So when you talk about vapor pressure, some liquids are easier to evaporate and some liquids are much harder to evaporate. Can you agree with that? Can you tell me something that's very easy to evaporate and then there is something that's very hard to evaporate?
Say gas is very easy to evaporate.
What is easy, sorry?
Gas.
Gas is already a vapor. Let's not talk about gases. Let's talk about liquids which can easily turn into a vapor or a gas. The
Like
distinction
gasoline.
between vapor and gas is sort of pedantic. Vapor can easily condense back, whereas gas is far into it. It's as much as that.
My bad. I meant like gasoline, like petrol.
Okay. Gas as in American gas. Okay. All right. So easy to evaporate, gasoline. Okay. And hard to evaporate. What is hard to evaporate? Example.
Mercury.
Mercury, very nice. Okay, mercury. And that's the reason why we use mercury in barometers, because it won't change. The amount of mercury you have won't change over. Okay. So this gasoline, we use the term is volatile because it can easily evaporate, whereas mercury is almost non-volatile. Okay. All right. And why a given fluid, a liquid is easy to evaporate or harder to evaporate, it concerns a little bit with chemistry and molecular structure. We won't go there, but vapor pressure is a defined quantity, that marks how easy or difficult a liquid is to evaporate. Okay, and how do we define this? So let's say we think about a container. We think about a container where you have a liquid. Okay, and if you just put a lid on it very tight and leave no airspace, you will just have a liquid, nothing else. But if you leave some space, let's say you have a liquid and then you have leave some space and then you have a lid and here is some empty space. What will happen is over time, the molecules on the surface, they'll start escaping the surface and they'll start roaming around in this space. We call this space is filled with vapor, which is basically molecules freely traveling around, as opposed to the liquid molecules, which are trapped in the or part of the bulk liquid. That becomes the liquid. And the interface is sort of like a free zone. We call it the interface or liquid vapor interface, where constantly liquid molecules that are part of the liquid escape and become vapor, and molecules that are part of vapor come back, condense, and they become part of the liquid. So there is a liquid vapor equilibrium at the interface. Okay. You're with me so far? We're almost there. Okay. Now, if you did an experiment with gasoline as your liquid, and one of you did an experiment with mercury as your liquid, and you both attach a pressure gauge into that space, the person who did with the mercury, what will you read as pressure? Brian, you said mercury, right?
Yes.
Okay, what will you read if you insert a pressure gauge with mercury liquid and a gap here?
It's not gonna make any vapor.
It's not going to make any vapor, meaning your gauge, pressure gauge, is going to read 0. It's going to basically not encounter any vapor molecules. It will think that there is nothing there, right? So some molecules or some liquids, they evaporate very slowly, which means they have a very low vapor pressure. And if you had put gasoline, like Rashid said, you're going to read you're going to read a higher pressure here because gasoline is very volatile. So vapor pressure is a quantity that essentially represents the liquid vapor equilibrium at a given temperature. If all else is same, temperature is same, the amount of liquid is same, the available volume is same, everything is same, it just measures which liquid has higher volatility. If it is more volatile, it will have a higher vapor pressure. If it is less volatile, it will have a less vapor pressure or a smaller vapor pressure. Make sense? So vapor pressure can again be looked up. It's a quantity that's been measured for many common liquids to know how easy or difficult they are to vaporize. But you should be aware that a liquid will always vaporize, and that extent is denoted by the vapor pressure. Before we close off here today, can only liquids evaporate? Can solids evaporate? Can solids go from solid to vapor?
Yeah, yes, they can. They can sublimate.
They can sublimate. Naphthalene, ice, we all see that. Like you just see naphthalene and then sometime back it's just gone, mothballs. So the solids also have a vapor pressure. You can define it the exact same way, just like there is a liquid vapor equilibrium. There is also a solid vapor equilibrium. So you take a piece of solid, you leave it in the bottom, and then you close the lid and attach a pressure gauge. If it is a non-volatile solid, you will see nothing. If it's a volatile solid, you will start seeing vapor showing up as pressure. And the vapor pressure for solids as a function of temperature has also been tabulated, and you can look it up. Okay. So to conclude this discussion, vapor pressure, or I'll write it. Yeah, vapor pressure PV as a function of T has been tabulated for both liquids and solids. Okay, I think I should stop here today. There is just still one more property called surface tension. It's not something we use a lot in this course, so I'm going to skip it. But I urge you to look at that section 1.9 self-study. Okay. So to conclude, the project is going to be finalized and posted roughly around 20 to 25%. I'll make sure it's not more than 25%. We are concluding chapter 1. There won't be a direct test of chapter 1 in the exams because the project is somewhat testing that. But chapter 2 is onwards, we're going to have it tested in the exam, and we'll pick this up on Thursday. Okay. What I urge you to do is to look at the end of chapter problems, go to the end of the book. If you look at chapter 1 for each section, 1.1, 1.2, 1. Up to 1.8, there are lots of problems. Just try at least 5 to 10 problems. Try picking anything from the book, and you should be able to do that because we have covered the concepts. They are really simple, really substitution of numbers, getting an answer. It's not at all complicated, but please try. And if you want help, please come talk to me. That's how you learn in this course. You won't be spoon-fed some example problems or kind of like do this. You have to do some self-guided example or problem solving. Okay, and come to me for discussion. That's more important. Understood? Try 5 to 10 problems from the end of chapter at the end of the book. Chapter 1 from end of the book. We'll meet on Thursday, hopefully in person. Thank you. I'll post these slides. Thank you, Elijah.